All right, AP Calc, here's the second video for section 2.4. Okay, so instead of talking about what's the limit as x approaches the asymptote of a function, what happens if we're just going to positive infinity, negative infinity, and we still have these kind of rational functions? That's what this video aims to underscore. So number 11. Maybe I can write it off to the left a little larger. You got 5x squared minus 3x plus 1 over 2x squared plus 4x minus 7. So there's a couple different ways to talk about this. The first way is to do like a graphing approach of things. But I want to show computational stuff first. So if you're approaching positive infinity, kind of the informal rule is, if I can plug into like a constant, for instance, the limit as x approaches infinity of a constant value c, okay? That equals the constant c, right? Because a constant function is basically like a horizontal line if you look at it from a y equals f of x perspective. So it's just going to be c no matter where you approach your x value. Additionally, if you are taking the limit as x approaches infinity of a constant value divided by some variable, so it could be x, it could be x squared, it could be x to the 90th power, it could be x squared plus 3x, blah, blah, blah. So I'm just going to say x to the n power, okay? If you have a constant on top of a fraction and a bigger power of x on the bottom, you can say, hey, there was a horizontal asymptote at 0, at y equals 0. I talked about it in the previous video. And it's going to be a constant divided by an infinite value, a value that just keeps getting bigger and bigger and bigger. It approaches 0. So if we can take the numerator of this fraction and the denominator of this fraction, do some algebra manipulation, and get just a bunch of constants and just a bunch of constants divided by x values, then we can do the plug-in of infinity. You know what I mean? Like say, hey, these parts zero out. All right. If that made absolutely no sense at all, let me show you what I'm talking about. The algebra manipulation is, I can multiply or divide the top and bottom of a fraction by whatever I want, just as long as it's done to the top, the same as done to the bottom. So if you look at 5x squared minus 3x plus 1, if I divided all parts by x squared, that would create a constant here, a constant divided by a power of x here, and a constant divided by a power of x here. I can now apply infinity to all three parts. But if I divided by x squared on the top, I got to do it on the bottom as well. So you divide by x squared, divide by x squared, divide by x squared. The x squareds cancel, leaving us with a constant. The x on top cancels with one of the x's on the bottom, constant over a value of x, and then a constant over the value of x. So this is the algebraic computation approach to computing limits as x approaches infinity. So applying it to the first one just gives me 5. Applying it to the second one on top gives me 0. And again, think of the metaphor, let's say I have $3 and I divide it amongst an infinite number of people. Even think about the number of people in the world. People would not get very much money. It'd be like 0.000000000 whatever cents. Same thing here. That zeroes out. That's the top of the fraction when you plug in infinity. The bottom's going to be 2 plus 0 minus 0. So the answer to number 11 is 5/2. That's the computational approach. The graphing approach is the idea that the infinite limit will be the value of the horizontal asymptote. So this right here has two vertical asymptotes at different spots. We can figure it out if we run it through the quadratic formula. I'm not going to do that though. I'm just going to say, if you look at the biggest power on top and the biggest power on the bottom, if those two powers match, x squared and x squared in this case, all you got to do is say it's 5 divided by 2 multiplied by the biggest, like this x squared here is going to dominate everything else out on top. So the x squared is the important part. The important part's being multiplied by 5. Same thing on the bottom. The x squared is going to dominate because you're squaring an infinite value versus just taking an infinite value times 4. 2 is being multiplied by that dominant value. Wow, okay. Sorry, I said a lot there. I think you guys remember the rules of horizontal asymptote. If the top power is the same as the bottom, use these to figure it out. Figure out the limit as x approaches infinity, which is the same as the horizontal asymptote's value. So look at number 13. The biggest power on the bottom is x. The biggest power on the top is x. Negative 7/3 is their coefficient. The limit as x approaches negative infinity versus positive infinity is going to be the same thing, because that's what a horizontal asymptote does. It levels things out at the asymptote and doesn't change things. So that's pretty cool. We've got that in our back pocket now. The horizontal asymptote equals the limit as x approaches infinity when it's a constant horizontal asymptote. Well, that's what a horizontal asymptote is. It's always constant. Does that work for 15? No, because the biggest power on the bottom is x cubed and the biggest power on top is x squared. So we have to, I don't know, we can do this same approach over here if that happens. The rule is you want to use the biggest power on the bottom to be the guiding force, because you don't want to divide by 0, which means I want to create at least one constant value in the bottom. Dividing 4x cubed by x cubed creates that constant value. So if I divide the bottom by x cubed, I have to divide the top by x cubed. The limit as x approaches negative infinity yields no different values than positive, at least in these cases. So this becomes a constant on the bottom plus 0. On top, though, this is interesting. You've got a constant divided by x, a constant divided by a power of x. That's going to be 0 minus 0. It equals 0. But we could have stated this anyway because we know that the rules of horizontal asymptotes are if the top leading power is smaller than the bottom leading power, its asymptote is y equals 0. All right. Now what happens if it's like 17 and 19 where the top is bigger than the bottom? Well, those are actually called slant asymptotes or oblique asymptotes. And you can figure this out by doing long division or by running it through this scheme right here. You know, we've done long division a few times this year. I think this is probably going to be better worth our time. Even though I love long division. Well, maybe not love. We're not there yet. Maybe I strongly like it. So the limit as x approaches infinity of negative x cubed plus 2x all over 2x squared minus 3. Look, I realize the biggest power is on top there, x cubed, but we have to keep it as trying to create a constant on the bottom, because I don't want to zero out the bottom. I'd much rather zero out the top. So I have to divide by the biggest power on the bottom to make this work, which is x squared. What you do to the bottom, you must do to the top. This creates a negative x plus 2 over x divided by 2 minus 3 over x squared. And it's the limit as x approaches positive infinity. So this is kind of what's going on here. If you plug in infinity, you get negative infinity for the negative x. This would zero out when you plug in infinity. This would still be 2, and this would zero out. So how do we process this idea of an infinite value divided by 2? Well, it's kind of like it's being multiplied by the constant negative 1/2. So the infinity, I mean, once you take a billion to the billionth power, then you can take that to the trillionth power, then to the trillionth power, and it never ends. It's sort of like, this thing's going to be infinity if I'm comparing it to any constant value through multiplication or division. It's still negative infinity. All right, so hopefully that makes sense. Now you can do number 19 pretty much the same way. Plugging in negative infinity kind of, you're just, if this were negative infinity, you would just use the rules of a negative creates a positive. Okay, so I won't go over number 19. I think 21 would be a better use of our time because it's got some stuff in there. Yeah, for sure. Not today. So number 21. Actually, can you guys see all of this? The limit as x approaches infinity. I'm instantly going to rewrite this as the cube root of the top divided by the cube root of the bottom. Or am I? Yeah, I think I am. The cube root of x plus x squared all over the cube root of x squared plus 1x. Okay, so really, it doesn't matter if there's a cube root to start with. What you can do is say, actually, I'm going to amend my statement. I retract. Sorry if you wrote this down already. I'm keeping it as one cube root, and I expanded the bottom here. Because here's what I'm thinking. The biggest power on the bottom is x squared. The biggest power on, and I could divide that by the top as well. I can just kind of pretend like the cube root's not there right now and do all this simplification inside of the root first. So you got 8 over x squared here, plus x squared divided by x squared is 1 on both the top and the bottom. And then this would be 1 over x. I believe there was a property that stated if you're taking the limit of a cube root, then you're allowed to take the cube root of that limit. It's basically, there's an interchangeability between the power or root of whatever you're taking the limit of and reversing it by finding the limit of the rational function inside. So then we can apply this infinite value to the first part. I will come over here because we seem to have a little more room right there. Yeah, so this is 0. So it's the cube root of 0 plus 1 over 1 plus 0. I'm zeroing out all of the x bottom constant top terms. So this is 1 over 1. The cube root of 1 is 1. Okay. One last one on this video because we're at 15 minutes and 46 seconds. It's the limit as x approaches infinity of sine of x. All right, I'm going to use a graph. Think about what sine does. It starts at 0. Sorry, guys. Didn't mean to leave you hanging. The graph of sine of x starts at 0. Let's just say all of these little increments represent pi over 2's. Okay? So it goes up to 1, down to 0, down to -1, up to 0, and just keeps doing that over and over and over again. Over and over again. So this is kind of tricky. What's the y value? Not values. The y value singular that x approaching infinity gives us for sine. Well, its range is from -1 to 1. Y is constantly oscillating between -1 and 1, and every little point in between is represented. So what you have to do is say, it's not converging to one specified y value. And it's not like approaching a direction forever. Like it's not just continually moving upward. If it were, we could say it's infinity. If it kept going downward, we could say it's negative infinity. If it kept approaching just 1, then we could say it's 1. If it kept approaching just -1, we could say it's -1. But because it is oscillating between -1 and 1, it never converges to one specified value or a trend value. The limit as x approaches infinity of sine does not exist. So, that's pretty sad. But that's life. Okay.